All right. Now Matthew will tell us about the simple essence of monomorphization. Please go ahead.
Thank you. We compiler developers have a bit of a problem, and that's that the low-level languages like x86 assembly, the makers of those refuse to add polymorphism to their language. And the same can be said for Java bytecode and ARM and LLVM. None of these support parametric polymorphism. And so when we write code that looks like this, where we have some function with a type parameter A, we need to do a bit of extra work to get this to compile down to that low-level code. There are a couple options for doing this. We can do the Java route, which is erasure. We can go the Rust route and do monomorphization, and maybe there are some other things. But if you remember the title slide of this talk, you'll know that I'm talking today about monomorphization. The basic idea of monomorphization is that we're going to be making a copy of each function for each type it's instantiated with. So if, again, we look at that function that I showed before, this ID function, it has a type parameter A, and we call it here twice, once with int and once with string. To monomorphize it, we're going to duplicate the function ID. We're going to have one specialized version ID int, one specialized version ID string, and then in each of those places, we're going to call the respective function, ID int or ID string. Monomorphization is a transitive transformation. So here we have added a function called twice. It calls ID twice, and it itself is called twice. We call it once with int and once with string. And when we do the translation, we need to duplicate both of these functions. We need to duplicate ID, and we need to duplicate twice. And we end up with a total of 4 functions. And of course, we need to change all of the calls to those functions as well. So you're all experts now on monomorphization. What do we do about this? And in particular, what do we do about that parameter f, which itself is a polymorphic function? That syntax there means for all z, z to z. Maybe you have kind of an idea of how you might do it, but it gets trickier. And you could be forgiven for thinking that this isn't even possible. It has been said that high-rank types cannot be monomorphized at all. It has been said that monomorphization cannot be done for higher-rank first-class polymorphic functions. It has been said that some polymorphism cannot be specialized statically, polymorphic recursion, first-class polymorphism. And this is what I would classify as glass half-empty talk. We are going to take a different perspective. We're going to say it is possible with some restrictions, and we're going to clarify exactly what those restrictions are. So today I'm going to be presenting a simple monomorphization method that supports higher rank and existential types. The key ideas here are that we are going to monomorphize a high-level language, and we're going to monomorphize via what we call a type flow. Now, when I say a high-level language, I mean our language is going to look like this. We'll have a source language which has polymorphic functions like we've seen, but then we'll have polymorphic enums like the option type, polymorphic traits like the show type, and then the target language is also high-level. It's all those same things, but in the monomorphic respective version. The type flow directed monomorphization has 3 steps: constraint collection, constraint solving, and specialization. The idea of constraint collection is that we're going to find which types flow directly into which type variables. So again, if we look at this original example, we can look at how the concrete types, int and string, will flow among the A and B variables. When we look at how twice is called twice, we see that int and string flow into B, and in the body of twice, B flows into A. And so we get a set of constraints that look like this: int into B, string into B, B into A. The next step is constraint solving, where we'll find which types flow transitively into which type variables. So we'll take those constraints that we had, and we can turn it into a nice-looking graph. And then we can clearly see, eventually, everything, both int and string, will flow into B and into A. And so we get a solution that looks like this. A maps to int and string, and B maps to int and string. And with this solution, we can take our original program, and we're going to replicate each declaration for each type in the solution. So we need to replicate ID for int and string, and we need to replicate twice, once for int and once for string. So this is nice, but it's also boring because this is what I showed at the beginning, and I promised higher rank functions. So let's take another look at that initial program. So the first step to handling this is that we need to translate it into our language. And the way we're going to do this is something like how Java represents functions. We're going to take that higher rank function f, and we're going to turn it into a trait. So we introduce this trait, we call it ID, and ID has an apply method, which has the same signature as that higher rank function. Then down below, we have ID itself, an instantiation of that trait. And then in the body of the app pair function, we apply that method of the ID trait to x and to y. From here, it's exactly the same as what we had before. So we're going to get some constraints out of the program. Specifically, from the app pair function, we can clearly see that int flows into x and bool flows into y. From the trait ID, we have a flow from the apply method in the trait to the apply method in all of the instantiations of the trait. And then in the body of the app pair function, we can see that x flows into z and y flows into z. And again, we do the same thing as before. We'll take these constraints, make a nice graph for the audience, and we will see how everything flows. Int and bool will both flow into z and into a. Int flows into x, bool flows into y, and we have our solution. The next step is to apply it to the program, and just as before, we'll duplicate some things. Here, the trait ID now has two methods in it, one for apply int, one for apply bool. The instantiation of ID also has those two methods, and then the app pair function will call the respective method of the ID trait. Now, this can handle all forms of polymorphism, and it's always handled in the same way. So polymorphic functions, polymorphic types, existential types, and higher rank types all can be handled in the same way. Now, you'll recall I had an asterisk on the first, or one of the first slides, and that's because we can't do it all the time. And when we can't do it is when we have polymorphic recursion. So here I have a program which exhibits polymorphic recursion. I have this function foo, and it calls itself. And clearly, first of all, it won't terminate. But as well, when we try to generate code for that we can't do that either, because foo calls itself with a larger type. So if we try to generate constraints from this, well, we can generate the constraints. But one of them is this box A into A constraint. And when we show this on the graph, we have a labeled edge with box. And what this means when we evaluate these constraints is that we're going to trace where int flows among these. So the first step, int clearly flows into A. But then when we go along that box edge, we need to apply that constructor to int. And so we go along that edge, and we get box of int. That's fine, but then we need to keep going along that edge, right? And we get box of int, and box of int. And it's clear that we have an infinite solution here. And there's no way to monomorphize that. And so we can generalize this kind of idea as a growing cycle. Any cycle which features a type constructor like that is going to be problematic for our monomorphization system. The nice news is that all forms of polymorphic recursion are uniformly detectable in this way. So they all show up as growing cycles. This includes polymorphic recursive functions, methods, and types, as well as what we call polymorphic packing, which is the case for polymorphic recursion in existential types. We have some meta theory. I won't talk about it, only to say that we have shown that our monomorphization system preserves semantics as we translate from the original to the monomorphized language. And we also have an implementation. Here you can see we have the input, we have a desugaring, and then down below there are some constraints. and the solution, and finally the monomorphized program. So in summary, I've shown a type flow-based monomorphization supporting higher rank types. We have 4 types of polymorphic recursion. We have a calculus and type system, which supports semantics preservation, as well as an implementation. If you want to learn more, there's the paper at that link. That's all. Thank you.
Hi, this is very nice. So you have this constraint solving algorithm. You generate the constraints. It either succeeds or fails. Do you have some other kind of crisp characterization of when it's always going to succeed? Or is it just throw it at the constraint solver and see what it says?
I mean, the constraint solver is very simple. So it's not like an SMT solver or something where it's very crazy. It's a fixed point computation, and if it has a cycle in this graph, then it's going a growing cycle in the graph, then it fails.
And I'm kind of getting at is, as a programmer, are there some more structured ways that I know that my program's going to work? Or
it's a non-local property, and so it's very difficult to determine.
Okay.
Yeah.
Thanks.
Hi, very nice work. So in 2019, we published a paper on language called Scilla, which is a system F. And then we have a follow-up paper which says how to compile it in LLVM, for which we built a type flow analysis, which seems very similar to you. That was 5 years ago. Did you compare to that? And if you did, what are the differences?
I'm afraid I'm not familiar with that.
Okay.
Have lunch with it. Have lunch together. So one way to deal with the polymorphic recursion question might be, instead of making a fresh copy for every data type, just make a, I'm sure you thought of this, just make a fresh copy for each different representation. Because after all, Intel, you only need one copy for functions that manipulate pointers, right? Yeah. Another copy for single precision floats, and so there's only a finite number of copies you ever need, and then you can close the recursion. Suddenly you can say, no exceptions, I can monomorphize everything. Wouldn't that be great? Did you? I mean, you must have thought of that and tried it.
Yeah, I mean, it would be great. I think this is a simple essence, and so that we consider that kind of thing just a little bit of an extension that is a little bit outside of what we call the essence. But yeah.
Okay, but this is a simple but wasteful essence.
Yeah,
right?
Perhaps, yes.
So make it. So the other question I had was to do with this is a kind of whole program analysis.
Yes.
Isn't it? So even if you've got a data type that contains a function, polymorphic function, well then every client of that data type out there in the world, you can't do any separate compilation at all with this system. Is that right? I mean, that is a problem in practice, isn't it?
That's correct. There's no form of separate compilation.
Okay, so does that mean, game over? Because the real world is full of separate compilation, isn't it? So
there are a lot of programming languages that don't have separate compilation. I mean, I suspect.
Mainstream use.
I want to say Rust. Yeah, okay.
Rust is a whole program compiler? Okay. Cool. Whole program. Yes. I know Milton. Yeah, that's right. And you get lots of juice from that.
Okay, we don't have time for other questions, sorry. So let's thank the speaker again.